All right, now let's go to the next one. A shave and a haircut. Suppose someone offers you all or nothing $100 billion in $100 bills if you are willing to count it out by hand. Should you take that offer? Now, it says all or nothing, so you have to count this out by hand without stopping. If you stop, you don't get the $100 billion, right? So that means that you have to take a dollar bill and you have to count it out over and over and over again. Now, that's pretty tough. I don't know how fast you can flip bills, but I'm going to say that it takes you half a second, right? Half a second to flip a bill, just on average, because you're going to be doing this for a long time. So you're probably going to start out fast. You're probably going to end pretty slow. Let's say it's on average half a second. Okay. So let's go back over here. So it takes you 1.5 seconds to count every bill. Okay, so you have 0.5 seconds, okay, for every bill. Now, wait, yeah, per bill. Now, how many bills do you have to count? Well, it said that you get $100 billion in $100 bills. So that would be 1 billion, actually 1 billion bills. So if we have 1 billion million, right, bills. Now let's see if you should take that, because these bills will cancel and we will get an answer in seconds. Then we'll convert our seconds. Well, let's see how big the seconds are, and then we'll start converting. So if we take 1 billion times 1/2, you get 500 million, right? Seconds. Now let's just convert straight to hours. Don't even joke about minutes, okay? So we've got 500 million seconds, okay? And then there's 3,600 seconds to 1 hour. So we take 500 million divided by 3,600. Then you get another big number. I got 138,889 hours. I have no idea how long that is, but you've got to do it straight. And I can't hold my pee for 138,889 hours. Don't know about you. Maybe you're willing to wet yourself for $100 billion. You do you. But let's see what that is in days, shall we? So let's take that times n line, 24 hours to 1 day. That all cancels. So we will get 138,889 divided by 24. 5,787.04 days. That's a long time. How many years is that just counting bills? Times in a line, 365 days to 1 year. Days cancel. So you take that number, divide by 365. You will be counting for 15.85 years. Now, the question wasn't how long does it take you to count it? The question was, should you take it? And honestly, that's up to you. Me, myself, I would not take that. I wouldn't take that at all. Uh-oh. Are we lagging? Go back. Okay, there we go. Same right slide. So should you take their offer? That's up to you to answer. If you're willing to count money for 15 years straight without stopping, I mean, I guess you could probably like promise someone money to feed you and like hold the bottle while you have to pee or something. Who knows? You do you. That's you to answer. But I can tell you how long it'll take you, and it is way too long. That's your answer. All right, now we have another one, hair growth. Shaving a haircut, right? So suppose your hair grows at the rate of 1/32 of an inch per day, which is supposedly accurate, says the internet. Letter A, find the rate at which it grows in nanometers per second. Because the distance between atoms in a molecule is on the order of 0.1 nanometers, your answer is going to suggest how rapidly the layers of atoms are assembled in protein synthesis. So this can actually get interesting. So we start with 1/32 inches per day. So let's go back here. Nirvana. So 1/32 inches, right? Every day. No, let's not do it that way. Right. All right, so we have 1/32 inches per day. There we go. And the question asked nanometers per second, right? So here is our goal. Nanometers per second. So we start at inches, and again, I always find that inch to centimeter because that's the only thing I've got memorized from English to metric at this point. So times in a line. Inch needs to go on bottom because it's got to cancel. 1 inch to 2.54 centimeters. Then we need centimeters to nanometers. Now, this really doesn't matter how you want to do this, but 1 centimeter is how many nanometers. Now, I've got the AP equation sheet right over here, so I will use this. You guys can also find this on your on the modules. I have the AP equation sheet, and it has metric things. So the easiest way to do this, in my opinion, is to do it in meters. So we have centimeters on bottom, right? 1 centimeter is 10 to the negative second meters. And a nanometer is 10 to the negative 9th meters, right? This isn't really going to work in unit analysis, though, is it? Because then the centimeters and meters. All right. Change of plans. We'll stick with centimeters. So 1 centimeter. So there are 10 to the negative 7th nanometers in a centimeter, I believe. Let's double check. Yep, 1 to the 7th. Sorry, 10 to the 7th nanometers in a centimeter. I was right. 10 to the 7th nanometers. Now, the reason I knew that is that centimeters is 10 to the negative 2nd, and nanometers is 10 to the negative 9th. You just find the difference there. There is a difference of 7. So, and centimeters is obviously the big one. So there are a lot of nanometers in 1 centimeter. So 10 to the 7th nanometers per centimeter. So we've got nanometers down. Got it. Centimeters gone, inches gone. Now we need days down to seconds. This is pretty easy. Day needs to go on top. You've got 24 hours in a day, and 1 hour has 3,600 seconds. And the nanometer and centimeter in the right spot. Sometimes if you do this wrong, they are flipped, and then you need to do it over again. You could always do some math to flip them, but anyway. All right, so hours cancel, days cancel. The only thing left are nanometers and seconds. So that means that our answer is right there in front of us. So we take 1 divided by 32, multiply by 2.54, multiply by 10 to the 7th, divide by 24, then divide again by 3600. And I got 9.1. Let's see, what are our sig figs in this? All we had is 1/32, so that's 2 sig figs, because 1 only has 1/32. That's got 2 sig figs. So we have to round this to 2 sig figs, which would be 9.2. 9.2 nanometers per second. Okay, now if we go back here, back to our slide, if the recording will catch up. Uh-oh, go back. Okay, so was it 9.2 nanometers per second? Now, the distance between atoms in a molecule is around 1/10 of a nanometer. So this is going to suggest how rapidly layers of atoms are being assembled in the protein synthesis. So if it's almost 10 nanometers per second, that essentially means that you've on the order, and if that gap is on the order of 0.1, correct me if I'm wrong in the discussion, that seems to be about 100 atomic layers of atoms bonded by molecules per second. I feel like my hair is working way too hard to grow. My body should convert that energy to something else. I take that back. It needs to work a little bit harder up here, a little less down here. I don't really like having to shave so much, but I could use some hair up top. Now, another bonus in the chat. If you shaved your head today on August 26th, how long would your hair be when we take our AP exam? Now, the AP exam this year is May 3rd, 2021. So the first person to give the correct answer in the discussion gets a stamp. So that's like, I'm throwing away points at this point. That's 15 points up for grabs for this bonus. But if the same person gets it, They were the fastest. So again, go ahead in the discussion and do the math real quick. If you shave your head on August 26th, 2020, how long would your hair be if you never get a haircut by May 3rd, 2021? All right, I believe this is our last, and there's a little glitch there on the recording. Okay, so last slide, I believe. We will solve a lot of problems without numbers. This class solves a lot of things with just bare bones units. Okay, so let's read this one. Let rho AL, rho, that's the Greek letter rho. It's a fancy looking P. That represents density. Rho represents density. So rho AL will represent the density of aluminum, and rho Fe that of iron. Find the radius of a solid aluminum sphere that balances a solid iron sphere of radius RFE on an equal arm balance. Now, that sounds kind of complicated, doesn't it? But there are a couple hints. First, they balance on an equal arm balance. That must mean what? That means that their masses must be equal, right? So we know that they are equal mass, but they are not equal density. We have two different densities. We know the radius of the iron sphere is RFE, so that is just a defined variable that we have. Now we will have to figure out the radius of the aluminum sphere, but it'll all be in variables. So I'll try to go a little bit slower on this one. But this is how we're going to solve a lot of problems in this class. So first, density, right? rho. That is mass divided by volume. Okay. So if we know that the mass AL will equal the mass of FE, then we should get those masses solved, right? So if we use rho equals MV, then M equals rho V, okay? So we can say that the mass AL equals rho AL. I'm so sorry. This isn't going to make it any easier on you guys if you can't read my writing. So I'll try harder here. Rho AL, okay, times the velocity AL. Okay, so all we're saying is that the mass of the aluminum ball is the density of the ball times the volume of the ball. And we can say the same thing for iron. MFE equals rho FE times V FE. Okay. So since they balance, we can say that those masses equal each other. So let's set them equal to each other, shall we? So we have rho AL V AL equals rho FE V FE. Okay. That's a good start. Now we're looking for radius. Density can't break down into radius, right? But volume of a sphere can break down into radius, right? Volume of a sphere is 4/3 pi r cubed. No, add 4/3 pi r cubed. Okay. Now we can substitute that in for the V for each of these quantities. So let's do that. Because they're both spheres, they both have, you can find their volume taking 4/3 pi and multiplying it by the radius of the ball. So we will have rho aluminum times 4/3 pi, the radius of the aluminum ball, cubed. And that will equal the density of the iron ball times, oh, sorry, I'm getting lazy over here. 4/3 pi, radius of the iron ball, cubed. All right. Now, there are a couple tricks right off the bat. You can see that there's 4/3 pi on both sides. That 4/3 pi is the same on both sides, so we can cancel that out. 4/3 pi on both sides cancels out. So let's say that the density of aluminum times the radius of the aluminum ball cubed is equal to the density of the iron ball times the radius of the iron ball cubed. So all we did was take the 4/3 pi out because there's a 4/3 pi on both sides. That means that it will be able to be divided out. So you can cancel it. Now we want to find the radius of the aluminum sphere if both spheres balance. So let's solve for the radius of the aluminum sphere. So we will divide over the density of the aluminum sphere and we'll take the cube root. So you have the radius of aluminum sphere equals the cube root of the density of the iron sphere times the radius of the iron sphere cubed divided by the density of the aluminum sphere. Okay. And that is your answer. Okay. Now, that is the style or the method that we'll use a lot in this class because we don't have numbers, so you're not going to get an answer. But if the scenario is true that we have a solid aluminum and a solid iron sphere, and they match their masses on an equal arm balance, then it doesn't matter their radius, because if we know the radius of one, we can find the radius of the other in every varying size of those spheres. So that's why this is important, is that it's not just for one instance. Say we gave iron a radius of 3 centimeters, then we could find it because we can just look up the density of iron and aluminum. But this formula works for every radius of sphere for iron or aluminum if the scenario stays true that they balance on an equal arm balance. So that's why we like to do problems like this, because you're not just solving one scenario, you're solving all of the scenarios. Let me get that slide to behave. There we go. All right, so that is the end of our unit analysis video. So go ahead and work those bonus problems. Hurry up and get those in the discussion board. And hopefully you aren't the only one to figure that out and it just goes to one student. It's nice to have some competition. But if one student gets all 3, you get all 15. All right, hopefully those were the first real mathy, physicsy notes that we've taken in these videos. So hopefully you're able to keep up. If not, if I was too fast or if I said something wrong, let me know in the discussion board. But you can also pause and rewind and watch a problem over again if I was too fast. And you can watch me rewrite it as well. So that should be able to help you. All right, next week we will be starting Chapter 2. Chapter 2 is kinematics. So that's stuff that you guys went over in depth with ASCII. So you guys should feel a little bit better about Chapter 2, hopefully. But we're going to start using some calculus. So heads up, calculus coming.